My name is Willy Baez. I'm a civil engineer major at Hostos Community College.
My name is Madieng Diao. My major is electrical engineering in Hostos Community College.
Okay, so as you can see, today we'll be talking about finding potential functions by simultaneous integration by partial differentials. Now, we would like to introduce, just say some words about what are we doing today, right? Now, conventional procedure of finding a potential function for gradient vector fields in space compromises a series of interleaving integrations and differentials. Now, basically, to sum it all up, right, this research suggests a simpler way, or a simple procedure, I would say, that uses only integration of partial differentials. We'll talk more about that. Now, before we introduce the subject, or in order to better understand this topic, right, we should define some very important concepts, which are 1, field, 2nd, gradient and potential function. First, we got the field, which is a region in which a point is affected by a force. Okay, for example, an electric field or a gravitational field. Okay, just for demonstration, if we have a pen, right, it will be affected by the gravitational field, right? We can use this room right here as a field, okay? Number 2, it will be gradient, right? The term gradient gives us the rate of change of a single variable. But if a function takes multiple variables such as x, y, and z, it will have multiple derivatives. The gradient of multiple function has a component for each direction. As we can see on our formula, the gradient of f is the partial derivative of f over dx, and plus, the partial derivative of f over the partial derivative of y, as we can see for k as well. Now, number 3, and finally, the potential function. Now, what is a potential function? It's a vector field, right, defined by f is equal to the gradient of small f for some scalar function of small f. Then it's called potential function for f, so the vector field is a potential and is also conservative. Now, I will give you pretty much the floor to my colleague Madieng Diao. He's going to explain the math and the procedure that it comes to finding the potential function on partial differentiations. Thank you.
So here we talk about potential function, right? But you guys need to know that before finding the potential function, we need to know if the field is conservative or not. It's really important, right? And the way we can prove that the field is conservative or not, we have some rules right here. So imagine we have a vector field f with mi plus nj plus p plus k. M just stands for the derivative of f in function of x, because remember what my colleague was saying, right? This is the gradient. So instead of writing down df and dx, I just use some notation which is m, n, p, and q, which stand for df over dy and df over dz. Now, how are we going to show that this is conservative? We're just going to take the derivative of p in function of y and try to see if it is equal to the derivative of n in function of z, and so on. So I will just prove one case, and you guys, if you want to prove the other case, you just can use the same method, which is easy. So let's see. Imagine we have this same vector field, which is f equal to mi plus nj plus k, right? And we need to find if dp over dy is really equal to dn over dz. Remember, I was saying that p stands for df over dz. That's why in the first equation, when we have dp over dy, we just replace the p by df over dz. And then we have the second derivative of f in function of dy and the dz. But here it doesn't matter the order. You can start by taking the derivative of, in function of y r in function of z. And then if we combine the derivative of x in function of dy, we just gonna have the n. And then we're just gonna go back to this formula. So basically dp equal to dy, dp, the derivative of p in function of y is just equal to the derivative of n in function of z. And you can do the same thing for dp over dx equal to dm over dz. So, and then we have the traditional scheme. So usually in all vector analysis book, right, this is the way we solve for potential function. It seems complicated, I know, but let's see what we're gonna have here. Imagine we have the same vector field, right? Mi plus nj plus k. So the way we're gonna find the vector field, first of all, we know that m stands for the derivative of f in function of x, right? It's the same notation, fx, or the derivative of f in function of x. So m equal to fx. Now, if we take the integral of this fx in function of dx, we're gonna have a new function, which is fxyz plus a constant. Maybe you guys gonna wonder why we have this constant, but if we go back, if we take the derivative of this, if we take the derivative of this function, right, the derivative of hyz in function of x is just 0, because this function doesn't depend on x, right? And if we take this derivative in function of x, we just go back to our main function, which is fx. So if you take this integral, we will have this new function. And also we know that f of y is the same thing as n. Fy is just the derivative of x in function of y. Then we can combine these two expressions. So we will end up with the derivative of y equal to xyz plus the derivative of h over y. Here also at each step we just use new functions, because at the beginning we have 3 unknowns. When you take the derivative of x, we end up by 2, and then at the end we're just gonna have 1. And then the last step, we're just gonna take the derivative of f in function of z equal to p. Then we can combine these two terms to have our expression for the potential function. But this way, it's kind of complicated, because you're gonna take the integrations, take the derivatives, replace it, and so on. So that's why we end up with this suggested scheme, right? For this one, we don't have to take the derivative. We don't have to replace. We just take the integral for each partial functions. Like for example, fx equal to m. If we take the derivative, we're just gonna have a new function px, xyz plus hyz. Then if we do the same thing for y and for z, we're gonna have these two functions. And then these functions is gonna be a constant. H, yz, jxz, and qxy. They're gonna be a constant. So our final function just gonna be equal to f xyz plus c. Now I should prove you guys why I was saying that these functions are constant. So let's see. Now imagine I combine these formulas, right here. We will have f of xy is equal to the first line for x, the second line is for y, and the last one is for z. Now if I let a vector r equal to f of xyz minus p of xz, so that means at each step I just move the p to the left. Then the new function, I just gonna call it r. And then if I make r equal to hyz, r equal to jxz, r equal to qxy, that's the last line we have over here. Now we assumed previously that this should be a constant. So if r is a constant, that means the partial derivative of r should be equal to 0. Like for example, if 2 is a constant, right, the derivative of 2 is 0. So if I assume that this r is a constant, so the partial derivative should be equal to 0. And now we're dealing with space, so the partial derivative of r in function of x, the partial derivative of r in function of y, and the partial derivative of z in function of, the partial derivative of y in function of z2 should be equal to 0. That's what we have over here. Now, how are we gonna prove this? So let's imagine we have a space, right, in 3 dimensions. So let's pick 2 points. I will first pick the A and the D. So here we already know that if you wanna find the work or the distance between A and B, doesn't matter the path we're taking, right? What matters is just the initial point and the final point. So if we do D minus A, if we do D minus A, it's gonna be really complicated to do the calculations, right? That's why we add 2 more points. So if we subtract the point D minus the point C, add it with the C minus B, add it with the B minus A. That's how we end up with this equation right here. So basically A is just the point at x1, y1, z1. And then if we take the partial derivative at each segment over here, like for example, from A to B, it's just xb minus xa. Between B and C, it's just yc minus yb. And between D and C, it's just zd minus zc. And then if we take the partial derivative, it should be 0. Then we end up with r x1, y1, z1 equal to r x2, y2, z2. So we just proved that this is a constant. So we can easily use our suggested scheme. Now let's see an example here. So imagine we have a problem right here. So F is conservative and we just want to find the potential field. So we're just going to use 2 different ways. The 2 ways we just talked about. Now for the first one, like I was saying in the beginning, M is just 1 over z, which is the derivative of f over x. Then we're just going to take the integral, right? 1 over z is a constant in function of x. Then we're going to have x over z plus jyz. So we're going to repeat the same process for y and for z. And then we end up by having x over z minus 4y plus h over z. And then we have to do the same thing again for the z component. And then after all this work, we will end up with this equation. This is the traditional scheme. The one I was saying is too long, right? Now, with the new one, we don't have to take the derivative. We're just taking the integral. And we already proved that the j of xz, hxz, and pxy just gonna be a constant. So this is really a good way to find potential function.
Thank you very much, Madieng. Now, in conclusion, I would like to mention thank you to Dr. Beninsky. I would like to acknowledge Dr. Beninsky. He's the one that presented this to us, right? And we were very excited because when we're taking linear equation, right? At the end of the day, it made it simpler for us as students, right? Now, in conclusion, I would like to say that it is proven, right, that the suggested scheme is easier to use than the traditional scheme for finding potential functions, right? Because it reduces the number of steps that are taken on the process, thus removing any confusion that the student might have as a student myself, as a student from Madieng as well. When this traditional scheme was mentioned to us and was proven, it was easier for us to find the potential function. Other than that, I would like to give some acknowledgments to the funding of CSTEP, to the CRISP, the CUNY Research Scholars Program, also to the funding of Hostos Community College, and the supervision, of course, of Dr. Alexander Beninsky. Further information, you can contact us, Madieng Diao and Willy Baez. And now, Q&A. I know. Please.
Yeah, I know at the beginning of the presentation, you covered a little bit the application. Can you go over the application of this?
Okay, no problem. So on this case, I want to go back real quick to both pictures on the traditional scheme and the suggested scheme. How can we apply this to real life? That's a really good question, right? Now, if we use the suggested scheme, let's say using what we mostly use it for, in this case, for computer science, right? Now this method, to put it into a program, it'll be really, really hard in space, right? Now, when we use, the suggested scheme, when we use the suggested scheme, it'll be easier to put it, to translate it into C++ or Java, wherever. It'll be much easier for us to do it.
How easy do you guys think it will be for students who are learning the stuff to use the suggested scheme?
I'm sorry?
Because you guys said it's easier for students to understand, so do you think it'll be something that's easily translated to other students who are used to seeing the other scheme to this?
Most definitely. Most definitely. Yes. Like, I'm telling you, it saved a lot of time on the test, actually. And it wasn't complicated. By the time that we understood this, and this came in, we were like, oh, this is heaven.
So would students have to learn the original way first before they can understand?
No.
Yes, this is the thing. If you're taking the vector analysis, right? In all books, you will have this one, the traditional scheme, and it's hard, it's long, and you have to integrate, then differentiate, so it's confusing. You have to take the integral for each component, for x, for y, and then for z.
But to answer your question, you don't need to know the traditional scheme, right? But if you know it, the new one will be so much easier. So much easier.
And then for the new one, you just have to take the integrals. So the components of x, you're just gonna take the integral in function of x, the one for y in function of y, the one for z in function of z. And all of these are constant, and then that's it. Just plug it. Thank you.
Any other questions?
Yeah, I have a quick question. So the suggested scheme, have you tried it in other computer applications like Python?
No, we didn't try it for Python. We didn't try it for Python. But we will do. That's a good question.
Yes.
Yeah, we will do it.
And I guess my question is, there's a lot of different things that you could have probably considered to do this whole process on. What made you select this particular topic?
Yes, because as student, right, when we were taking calculus 3, this topic was very, very complicated, and confusing for all of us. So by doing this, it's like we're gonna help, our peers, that we take calculus 3 in the future to have this easiest way, and they will not gonna struggle, about potential function, because potential function is very important. You will do this in electromagnetics and physics, in many, many fields, So if you have the simplest way to solve this, you'll be fine.
So one last question. So have you thought about publishing it? The findings?
Oh.
So let me speak on that. So Dr. Beninsky, right, and I forgot his name. What was his name? They had, Dr. Beninsky and a colleague, right? They had an unpublished. They made it, but only in plain, right? XY, right? They had an unpublished paper on it. If it does come to a reality, yes, we would like to actually publish it.
It's going to be challenged.
I'm sorry?
It's going to
Yes.
be
Oh, yes, actually. I would like to talk with Thomas, how do you call it? Thomas? Calculus 1, 2, 3. I would like to talk to him about it, yes.
Interesting.
Thank you.
Thank you very much.